here's a really novel example, and I'm trying to remember. This one might appear on the homework, although if it doesn't, don't get mad at me, I hope. But anyway, I think at one point I had it on the homework. It might still be there, but we're going to do it anyways. It says, suppose that a time machine uses an amount of energy proportional to the time t traveled. The energy used is also proportional to the square of the mass m transported. Use this information to write a formula for the energy used. Let's start with that. Well, let's see. I think, let me translate that first statement because we're talking about energy. I think E, maybe uppercase E, kind of like Einstein used for E equals mc squared. But now we're talking about time travel, which is obviously fake, right? As far as we know, at least. But anyways, if it's saying energy use is proportional to time, I could restate that as a proportion. There it is, right? But then it's saying energy use is also proportional to the square of the mass m. So if I want to write that as a proportion statement, it might look like, whoops, that didn't quite turn out there. E is proportional to m squared, like that. And both of these, like if I were to look at this one, I would say, like, kind of the assumption here when I say energy is proportional to time, I'm assuming I'm not changing the mass, right? Like if I compare two objects, same mass, but one is simply transported a further amount of time, maybe into the past or in the future or whatever, right? Depending on what movie we're thinking of, or TV show, I guess. I don't know. So this assumes constant mass, and assuming constant mass, I would say, well, there must be some proportionality constant that the formula would look like this. And maybe I'm actually going to call this one K1 just for fun, because we got kind of two different situations here, and they'd have different constants. Because like this one, in turn here, I'm talking about what happens if I change the amount of mass. If I double the amount of mass, it's obviously going to cost a lot more energy because it's proportional to mass squared. It would actually mean it would cost 4 times as much energy, would make sense. And that would be reconciled with the equation for some proportionality constant K2 times mass squared. But now, if we're saying, because we're asked, use this information to write a formula for the energy used, which, okay, that's a little vague, but I'm going to assume that we're being asked for a formula that is able to take into account both changes in the amount of time traveled and differences in the amount of mass transported through time. So we need to combine these in some way. Well, remember I said this one assumed mass was constant, this one assumed time was constant. Probably whatever I have, I think it makes sense, and you can tell me if you think this is wrong, that if I kind of just multiply t and m squared, and then maybe throw in a different, I'll just put in a k without a subscript, a different proportionality constant, if it can even be called that, or just a different constant, that this would cover. In other words, if I have a particular value of mass m, then this k times m squared would actually be what this k1 is. And in turn, this k2, if I had some particular value of t, would be whatever that is times this k would be what k2 is. I hope this is not getting too crazy mathematical again. I've sent some other examples. Please don't go run screaming from this class. Sometimes I get a little mathy up front, but I don't want people to be too tremendously scared from it. I want people to recognize some stuff is simple, and I'm showing you something here, right? So again, don't let the symbols get too frightening, because they often do. They scare me, actually. Maybe that's why I'm saying that. But anyways, this I think incorporates both ideas, because if I doubled, say, the amount of time, this would double. If I doubled the amount of mass, this would quadruple, provided time stays the same. So this kind of covers both of these proportions. I'd still need to have some like value for a different value for k, because I just don't know enough information based on knowing about proportions to know what that is. That's kind of the way proportions work. But now we're asked, would it cost more energy to travel twice as far in time, or to increase the mass by half? So if I say twice as far, if I'm saying like 2 times the amount of time, so I'm just going to say 2 times t, I think clearly indicates 2 times the amount of energy. So I'm kind of writing this in a weird, this is not really like official math notation, but clearly for doubling the amount of time traveled through, I don't know if that's the right word for that, talking about something that's impossible, right? It would double the amount of energy. But what would happen if you merely increased the mass by half? Well, I'm going to argue, so if you say 2 times the mass, since its energy is proportional to mass squared, my thinking is that you'd, oh wait, I said 2 times, that's a mistake. I meant to say, because it says, what does it actually say? It says increase the mass by half. So really that should be 1.5 times, right? Increase mass by half would be multiplied by 1.5. So I'm going to say 1.5 applied to m. This is really bad notation, but hopefully it makes sense. But what's going to happen with the energy, because energy is proportional to mass squared, is it's actually going to multiply by 1.5 squared times energy. And that might make sense because, like, if I thought about this as like a paired situation here, if I thought about like an E2 over an E1 and how that relates to possible change in masses, it would be an M2 over M1 squared. And if I'm talking about just increasing the mass by 1.5, that would mean that M2 over M1 as a ratio is actually equal to this 1.5, and the ratio of the energies would therefore be equal to the square of that. So that's kind of like one way of seeing, if you really enjoy math, that's one way of seeing why this is correct. But physicists tend to get a little conceptual about this. But 1.5 squared, I think, is equal to, I believe that's equal to 2.25, right? So this is really saying 2.25 as a factor of increase on the energy, which is more than it was for simply doubling the time. So I think it would cost more energy to increase the mass by half, which really illustrates that squared scaling, in other words, being proportional to the square of something, results in a more dramatic increase when you increase that something. So let's check the answer, and there it is. We got E is equal to KT m squared, as I wrote, and the increasing mass by 1.5 results in an increase by a factor of 2.25, which is obviously more than the doubling that we're comparing to for more time traveled.